Hi, my name is Sobi Bark, and this presentation is about the scaling of the magnetization inductance. It is the answer for the questions that I have posted in LinkedIn in the group of Professor Binyakov. So the question that I have posted in LinkedIn, it is about how we can find or design the magnetizing inductance if we increase the number of turns by m times. So before I give you the answer, I would like to explain why the reasons and the reasons why I have posted these questions. So I think everyone that is active in the power electronics groups in LinkedIn and also in the IEEE power electronics community, they heard at least one times by what is called the scaling law. So for those who don't know the scaling law, it has been developed and proposed first by Manik Tala. It has been developed to design the magnetics for boost and back converter, and recently it is extended by Mr. Nicola to design the magnetics for LLC and DAB. So what says this scaling law? It says that if the power it increases by n times, then the inductance, whatever it is, if it is the magnetization inductance or the inductance of any given inductor, it will decrease by n times. So here we'll see how it cannot give you the right design, and it is completely wrong. We'll see through these questions how we can find the inductance when the power it increases. So here I have only mentioned and I have proposed to increase the number of turns, but later on I will also give the answer for another questions when the current increase or when the current through inductance increase, and through both questions you will understand how the inductance or the scaling law, the correct scaling law of the inductance when the power increase. So let's start. So let's suppose you have a transformer that have n turns. Here I will just put the primary. So this one is your transformer. And the questions I have asked you is to increase the number of turns by n times. So what is the reluctance model of the magnetization inductance? Everyone, I think you know this equation or this expression. So it is function of the permeability, mu naught times mu r, where mu r is the relative permeability of your magnetic material, and n is the number of turns, and AE is the cross section, and LC is the mean magnetic path of your transformer. So this equation, when you look at it, it will not explain you what is the magnetization inductance. It is mathematically correct, but physically it is not correct. So the right equation that can give you or explain you the magnetization, it should reflect the Faraday's law and the Ampere's law. So what is the correct equation? It is the following. And this. So this one, it gives you Ampere's law. This one, it shows you Faraday's law. And for the transformer, both law exist. a transformer cannot operate, cannot work without both laws. It's not only Faraday's law, it's both Faraday's law and Ampere's law. So when you see to the Faraday's law, you see that there are two variables, the number of turns and the cross section. These two variables, they are independent. Now look to the Ampere's law. It is function of the number of turns and the magnetic path, or the mean magnetic path length. These two variables, N and LC, they are dependent on each other. So if you increase the number of turns, the magnetic path, it will increase. And this is the main mistake that all the people have made, and it is the main issue or the main point that all the people did not understand. If I tell you, you multiply the number of turns by m times, then for sure and forcefully the magnetic path, it will change, and you have to consider that. Now let's see how it will be changing. So here, let's suppose that this length, it is equal to LW, and now I asked you to increase the number of turns by m times. So this length also, it will increase by m times. So let's define first what is the mean magnetic path. The mean magnetic path, it is this one. It is the mean length of the magnetic path. So the flux, it will go through the center leg, and it will be divided between the right and the left side, and then it will close the path. So that one is LC. And let's denote this one, LW, is only the length of the winding. So the full magnetic path, or the length of the magnetic path, it's the sum of this LW plus the length, the remaining length. So it is LW here and plus the remaining one, and it applies for both sides. So it is very easy to make it in an equation. So we can start to develop this one. So the first thing that I will do is just, and this is the easiest one, is to calculate the magnetic flux density B. So if I increase N by m times, so this N1 is the original number of turns, and N2 is the new number of turns when I increase by m times. So N2 is equal to m N1. So what will happen to the magnetic flux density B? Of course, this everyone can get it. It will be divided by m times. This is clear from Faraday's law. So B2, it will be equal to B1 divided by m. This is the first result that everyone, I think, can understand. Now, in order to understand or to determine the magnetizing inductance, we need also to look to the magnetic field. And when we look to the magnetic field, I mean this by Ampere's law. So if I increase the magnetic or the number of turns by m times, the magnetic length, it will increase, and also we have to calculate what is the magnetic field. So in order to understand this, I will suppose that I will increase the number of turns by 2 times. So what will happen now? So here the original magnetic field, H1. So it is equal to N1 times the magnetizing current I1 or IM1. It will be divided by the length LC. Now I have increased the number of turns by 2 times. So H2, it will be 2 times N1 times IM1 and divided by, so I will, the original length